This is video 28 in the lecture on the design of reinforced concrete beams. This lecture deals with the representation of the reinforcement or the detailing of reinforcement. The detailing of reinforcement is described in the ISO 3766, dealing with construction drawings, simplified representation of concrete reinforcement. It gives you a method for specifying dimensions, coding system for bar shapes, a schedule of preferred shapes, and a shape schedule and bending schedule. On a drawing, there should be put on at least the concrete strength, the exposure class, type of reinforcing steel, a bar mark, a number, a diameter, a shape and a position, the distance between bars and the overlap. The shape code, according to ISO 376, is given by two numbers, X and Y. The first number is indicating the number of bends, but hooks not included. So the first X is the number of bends. The second number comes from this table. And we just see now how to use this table. First of all, a shape, the dimensions in the shape is always outside. So dimensions are outside dimensions, always outside. And the radius, the diameter of the radii, they are always inside dimensions. So a radii is inside. There are just the two rules. Now let's look at this shape. This shape here has two bends. So X is 2. And the Y number of this shape is 6 because the two bends are not in the same direction and the angle here is smaller than 90 degrees. So it's 6. Directions not the same. So the shape number is 26. Another example, we have here two bends. So the number starts with 2 and the two bends are in the same direction. So it's a 5. So the number is 25. You see that the hook, the little hook here, we do not count as a bend. In this example, we have 4 bends. So the number starts with 4 and they are all in the different directions, or they are in two different directions, the bends. So we have then 44. That's the 4 in the table. Direction not the same. And the bends are 90 degrees. And another example is this one. This is not in the list, so it starts with a 9 and it ends with a 9. So it's number 99, this type of shape. And in a bending schedule, you indicate the shape by a small representation. You don't really show the radius here, the radius. The dimensions are always outside dimensions, A, B, and C. So shape 21, that's where shape 21 is coming from. And then here comes the number A, B, C. And so it goes on. For each shape, you can have some numbers in it. To mark a rebar on your drawing, you have different elements. The first is a bar mark. Then the total number of bars, the bar diameter in millimeters, the spacing in millimeters, and the position in the component or construction part. This is optional. This is not necessary. It's like a T for top, or a B for bottom, or an F for FF for far face, of an NF for near face, and so on. And then the shape code of the reinforcement that we have seen just now, this is the shape code. So how do you mark your bar? It's marked by, for instance, bar number 3, 19 bars, diameter 20, spaced 20 centimeters, they are laying on the top. That means the first layer. And the shape is 13. This is the full indication. Most of the time it's used like that. It's a little bit shorter. If the drawing is clear where the bar is situated, then they use the shorter form. And even nowadays we use just the number and then 19 diameters 20. We even use a very short notation. But preferably you should use the complete notation according to the ISO. A nice explanation of how to represent the reinforcement is done by the Technische Voorlichting 260 of the WTCB, or in French the CSTC. These are two nice complete documents. And what's coming now is as a reference has the document, the TV260. You can see here a typical picture of a rebar, and this is the rebars coming in rolls. Of course, this is for small diameters, not for big diameters. Then each rebar is marked with marks. It's not by accident, it's on purpose. You have different types of rebars of reinforcement. You have hot rolled, it's always indicated by BES or BETS. And then you have the cold formed reinforcement bar, it's BEES and BERS and DEBS. Most commonly used it's BES, BE500S. And the BE500S, you can recognize it because it's hot rolled about if you take a cross section, you will see two elements protruding. These are those skew things, like you see here in the picture. The TS, you see that you have a double protruding system, then you know you have a BETS, and then it's squared. You have the BE500ES, the cold formed, you can see because it's 3 times 120 degrees, so that's the best thing to recognize your steel between hot rolled and cold rolled. The cold rolled formed of cold formed, I have to say, is always 3 times 120 degrees, and on the marking on the rebar you can see what type of rebar it is. This is a typical cutting tool where you cut the rebar. This is when you do the bending on site, not in a factory, but when you do the bending on site, this is a tool to bend rebars. And you can appreciate now that if you have bends always in the same direction, it's much easier to use this tool. Also use bends always in the same plane. Don't use bends in different planes because you cannot do it on site. This is a typical element for walls where you can put rebars in it, close the shuttering, and when everything is poured, you open the shuttering and you can pull out the rebar by means of an extension tool where you can put another rod in it and you can ply it over. This is for safety on each side. You should never have protruding rebars sticking out somewhere where it can hurt people, so you always should have a protection element on top of it. You can have also protection elements like this, and it's a typical element. Now this is a nice example of a beam with stirrups and 4 diameters, and someone made a drawing like this, and it all fits in. He must have a concrete cover of 25, and the stirrup is 12 millimeters, and the bar diameter is 25, and the distance between, the clear distance between the bar diameters has to be 25. Good. I prefer 40, but this is now an example of 25. And this guy making this drawing thinks this is fine. This is now working out perfectly. But on site, what will happen? On site, when there is somebody putting the reinforcement steel into the shuttering, knows this rule, so it's a very good guy. He takes care of the concrete cover. He knows it's important. He knows it's important that the clear distance between the bars must be 25 and not less than 25, but he cannot put all the rebars in the same layer because that stirrup is bent. So this is taking care of the clear distance and of the concrete cover, but the lever arm will be less than what intended is. Not much, but it will be less. Another way of doing it is that you put them all in the same layer. You take care of the concrete cover, required concrete cover, but the clear distance now is less because you cannot move it over. So the clear distance is now less than 25. So this will be a problem for concreting. So it's no good. Or another way to do it is you put the rebars in the same layer. You put the 25 distance, clear distance, but now your concrete cover is less than 25, which is no good. So whatever you do, it's no good. So take care if you make a drawing like that, that you should take into account the bending radius. Rebar should always be kept in place because of the pouring of the concrete. They can shift, and they should not do that. So for keeping them in place, you put some little wires, chicken wires, and to tie them. You also have elements to make sure that the concrete cover is there. So it's a distance indicator. You can have elements for, this is also a distance indicator or distance tool. You have small girders. You can have them in all shapes. They are in fact nothing more or nothing less than making sure that the distance between two fabric meshes are kept. Then you have all types of little tools in steel to put your rebar on so that you are sure that you have a certain distance. For a wall, you can use elements like B and C. You can use it's in plastic holders. You can use holders where you put the bar in so that they are fixed and that they are not that they cannot move around during concrete pouring. These are all types of distance tool. Let's put it this way. It can be of cement or of concrete, plain concrete, of course, or of plastic, concrete or plastic. You can also use another rebar if you have two layers of reinforcement and you want to make sure that there is a distance between those two layers. Then you can use, in fact, small pieces of rebars, and they guarantee you the distance between the two layers. You can use coupler boxes. This is when you have large bars and you want to have a large in length rebar, you can, and you have to pour it in two sessions, then you can have a coupling between those two. This is for thermic isolations for a balcony. This is a typical star box element. It's a box in PVC. You put it into the wall, and when the concrete is poured, you click open the box and you pull out the reinforcement to continue with the slab. This is a typical example of a dowel when you have two elements where the bending moment is 0, but the shear force, you need to continue the shear force. Then you have a typical dowel. You see that the blue one, this is not fixed, so the two pieces can move in this direction. For a column or a wall, if the distance between two vertical bars is bigger than 150 centimeters, then this is not allowed. The distance must always be smaller. And when it's smaller, then you don't need to fix the rebars. When it is bigger than 150 millimeters, you have to fix the rebars here with a thing like that. This is to avoid that those bars are flipping out of the construction. You have different possibilities of keeping this distance of 150 millimeters. So every 150 millimeters there must be a rebar. You can have different systems. You can have two different stirrups. You can have one stirrup and then a small element surrounding the two others. This is shear reinforcement for slabs. This is a typical way of reinforcement of a beam connected to a slab. You have the stirrup doing this, very well anchored in the compression zone, and you have the tension reinforcement on the bottom. For a slab, you always should close the slab with a stirrup with a length of at least 2 times the thickness of the slab, and in the corners always there must be at least one rebar. This is a closing corner. This is a typical reinforcement of closing corner, taking care of the bending moment on the outside. And this is a typical reinforcement of an open corner. When a corner is opening, then you see that this is a stirrup doing that, and this is a stirrup doing that. And this is the best way of reinforcing a corner, because it's a mechanical interlocking. This bar is needed when the forces are relatively high. So for high constructions and things like that, this bar is needed because you have tension here on this side. This is a typical reinforcement of a wall and a slab. This is the needed reinforcement on the edge of the slab. This is when it's a wall is continuing in the second level, then you should have the reinforcement of the slab continuously. You put the reinforcement already there before concreting the slab, and then you go on with the next part. This is the lap length of the reinforcement. The same happens here. It's the lap length of the reinforcement. This is a typical example of a retaining wall. It is preferred that a retaining wall should always have this level of this rebar on 45 degrees because of the concentrations of stresses in the corner. So if you look at this in practice, it looks like that. This is a typical example of a retaining wall, the reinforcement in the corner of a retaining wall. Then we should take care of, when you have a slab or a beam, that at least the lap length should be LBD when a beam is coming onto a support left and right. When you have torsion, let's put it this way, if you have a stirrup, you should close the stirrup like it's indicated here, but you should not close it like it's mentioned there, like this, just in a straight angle. You should not close the stirrup like that. The stirrup should be closed under 45 degrees. Or this can also be done if at least one length is overlapping. This can also be done. This is the most commonly used when a beam and a slab is connected. It's like this. When you have torsion, well, the longitudinal bars should be so arranged that there is at least one bar at each corner, and the others being distributed uniformly around the inner periphery of the links with a spacing not greater than 350 millimeters. So that's when a beam is under torsion. You should have reinforcement all along. This is shear reinforcement for a beam. So these are all kind of rules. For instance, the distance between two stirrups must be smaller than 0.75 the effective depth, and the distance should always be smaller than 600 millimeters. As a rule, as a general rule, I prefer that all bars should be at least or the maximum 300 millimeters from each other. So I take a distance not more than 300 millimeters. If I use that, then I'm sure I'm complying with all those rules. This is stirrups for a slab. You see it's getting quite complicated, so avoid stirrups and slabs. This is also typical. This is a slab and this is a column, and this is the way how to position stirrups in a slab for punching shear, and you see that you have all kind of rules that you have to obey to. For a column, in each corner there shall be one rebar in longitudinal direction. The minimum reinforcement is 10% of NED divided by FID, or 0.2% of the concrete section, whatever is the greatest. The maximum is 4% of the concrete surface, of the concrete area, of cross section, the concrete cross section. The diameter in the corner should be at least 1 diameter 12. So don't bother in a column with diameter 10, it's not allowed. And the stirrup, the spacing of the stirrup is the minimum of 300 millimeters, the minimum size of the column, or 14 times the diameter of the stirrup. So the distance between the stirrups is 300 millimeters, or the minimum size of the column, for instance, a column of 200 by 200, then the minimum distance is 200, or 15 times the diameter. If you use a stirrup diameter 12, then it's 15 times 12, the minimum distance between the stirrups. If you have a continuous column and this is a slab, then over a distance of A, you should have stirrups with a minimum spacing of 180 millimeters, or the minimum size of the column times 0.6 of 9 times the diameter. This is a confinement reinforcement needed on top of and on the bottom of each column when it's reaching a slab. For a wall, the vertical spacing must be smaller than 400 millimeters or 3 times the thickness of the wall. Horizontal spacing is smaller than 400 millimeters. This is a little bit misleading. Why? Because if the wall is loaded in this direction, in the direction of the wall, then there are other rules coming into place, because then it's the rules of a slab are then valid. But if it's a real wall, then you see on top it's always 0.2% of the total cross section. And next is for a building, you need some reinforcement chainage, a real chainage. And when you have an individual column, then the chainage should be enough to take over 20 kilonewton per meter edge of the building, per meter facade. When you have and this reinforcement on the facade should be, is a chainage reinforcement, should be able to take 70 kilonewton and must be situated within 1.2 meters from the edge or from the facade. In the middle, when it's not a facade, it's 20 kilonewton per meter. So the chainage reinforcement is important for the total stability of the building. And this is then a a typical example of a reinforcement drawing. I borrowed it from Gilbert van den Borre. And this shows how a cross-section of a beam is indicated in reinforcement. I've seen that Gilbert has not used the typical shape numbers, but he's using a small drawing for clarity. So that's also allowed. But you will see, for instance, that on the bottom reinforcement, it says it's 4 times 25 meters, 17 meters long. And then he indicates for the 17 meters, how do you achieve that? By 2 times 5, 1 times 7. This is another example of a beam with its connections to the neighboring parts. Then a cross section to clarify how the reinforcement is put. You know now how reinforcement drawings look like. See you in next lecture.